All right, Matt 2, here we go. We got lesson 5.2.1. We're introducing it. So this is the first part of the lesson. We're going to do it in two parts. And we're going to just talk about simplifying radicals. Okay, so the first thing is, what does a radical represent in the first place? We're just going to use root 9 to explain what it means. Well, we know that root 9 is equal to 3 because a radical, such as root 9, this just means what number multiplied by itself I can't spell today. Multiplied by itself equals 9. So what number multiplied by itself is 9? 3, because 3 times 3 is 9. So what we see here is that the square root is really the opposite operation of squaring. So the square root is the opposite of squaring. Can't spell again. All right, so that means kind of like how multiplication and division, how they kind of undo each other, and then like addition and subtraction, how they undo each other. Squaring and square rooting would undo each other because they're opposite operations. All right, so we have perfect squares. Perfect squares are where it's an integer value, like a whole number value answer. So like the square root of 1 is 1 because 1 times 1 is 1. Square root of 4 is 2 because 2 times 2 is 4. Square root of 16 is 4 because 4 times 4 is 16. 36 is 6. 6 times 6. 49, 7. 400 is 20 times 20. Okay, so those are what we call perfect squares, and they always reduce to kind of like nice integer values for that. Now, sometimes we get numbers like square root of 8. There is no nice integer value that you can multiply and get 8. But there is a number out there that you can multiply by itself and it would become 8. But this is what we would call an irrational number. Irrational numbers are kind of like pi. You know how pi is like 3.14159265, you know, that whole thing. And we know with pi, it keeps on going and it never repeats itself. That's what an irrational number is. So when we have numbers like 8 down here, the square root of 8, it's not a perfect square. It's like pi. It's irrational. It's impossible to write the number down because it keeps going, never repeats itself on the decimals. But what we can do is we can simplify it by pulling out the perfect squares that are the perfect square factors that are inside of it. So like the square root of 8, it has a perfect square inside of there because the square root of 8 is the square root of 4, which is perfect, times the square root of 2. So square root of 8 is equal to root 4 times root 2. And we just set up here that root 4 was 2. So this would become 2 times the square root of 2, or 2 root 2. And that's the simplified form because we've taken out the perfect square factor. So the perfect square factor was 4. We took it out. It became 2. 2 root 2. Now it's simplified. Same thing with 20. The perfect square inside of 20 is also the square root of 4 because this is the square root of 4 times the square root of 5. So we've got a perfect square factor. So we're going to take that out. And then the square root of 4 is 2. So this would simplify to 2 square root of 5, or 2 times the square root of 5. Now, as you get to bigger numbers, sometimes it's harder to just look at it and recognize what the perfect square is inside of it. So what you can do is make a factor tree of the numbers to find out what your perfect squares are. So for instance, on this problem we already did. 8 is 2 times 4. Maybe you don't recognize that 4 is a perfect square. 4 is 2 times 2. So we do the prime factors. And since we're looking for squares, that's a number multiplied by itself. Well, here's a number multiplied by itself, 2 times 2. and then we have a 2 left over. The 4 we don't count because it became 2 times 2. And I always like to say that couples, it's like Friday night. Couples go out, and the single stays inside of the root right there. So 2 root 2. Same thing with 20. If we broke that up maybe into 2 times 10, and then 10 is 2 times 5. We've got a pair of 2's, so there's our couple, and we got a single 5 left over. So this pair of 2's represents 2 times 2, 4. So we're going to make that come outside and get the 2 right there, and then we've got a 5 left over. So this is kind of what you do when you don't automatically see the perfect square in there. So let's say that you don't see the perfect square inside of 75. So maybe you go, oh, I think 5 goes in there, and it goes in there 15 times. And then 15 is 5 times 3. Oh, I did have a perfect square. It was 5 times 5. So couples go out, the 5 goes outside, and the radical that remains is 3. All right, keeping on working. This one, I see that it ends with an even number, so 2 has to go in there. So this would be 2 and 49. But wait, 49 is a perfect square. That's right. It's 7 times 7. So I got a pair of 7's and a 2 left over. So it's like Friday night. Your couples get to go out, and your singles have to stay home. This example really doesn't make sense because I'm married and we never go out on Friday night. But anyways, you get the point. So couples can go out, singles have to stay home right there. 96, maybe you don't see the perfect square in there. Perfect square is 16, but maybe you don't see it. So let's break this up. This would be 2 and 48. And 48 is 2 and 24. And 24 is 2 and 12. Oh gosh. And 12 is 2 and 6. And 6 is 2 and 3. Holy cow, look at all those 2's. We do have pairs. I got a pair of 2's here, and I've got another pair of 2's here. And then I've got a 2 and a 3 left over. So what happens when we have multiple things? Remember, all these are factors. They've been multiplied. So if I take more than one thing out, I just multiply it. So I'm going to take out this pair of 2's, and I'm going to take out this pair of 2's. Inside the radical, I've got a 2 and a 3 left over. So there's 2 times 3. Since everything's a factor, if we have multiple things coming outside of the radical or multiple things staying in the radical, we just multiply them together. So here's 2 times 2 is 4, and we get 2 times 3 is 6. If you really knew your multiplication tables really well, you would have already known that this is 16 times 6, and 16 is a perfect square, and 16 is the perfect square of 4. So you could have done it like that if you would have noticed it. Now, in problems like this, you might have done like, I don't know, 2 and 15, and then you've got 3 and 5. There are no singles left, or there are no pairs. Everything's a single for this one. So this means that it is already simplified. Root 30 cannot further simplify. We would just get 2 times 3 times 5 left over. It's still root 30. It doesn't simplify anymore because there's no perfect square in factor inside of 30. For 45, you might have done like 3 and 15. And then 15 is 3 and 5. Do you have a pair? Yep, I got a pair of 3's and a 5 left over. So this would be 3 square root of 5. 72. Let's see, 2 and 36. Perfect square right there, so maybe you don't see it. This would be 2 and 18. This would be 2 and 9. And 9 is 3 and 3. So I got a pair of 3's and I got a pair of 2's. And then I've got a 2 left over. So the 2 can come outside, the 3 can come outside, and then I've got a 2 left inside. So everything that comes out, we're just going to multiply it because remember they're all factors. So I end up with 6 square root of 2. 144. Maybe you're just coming along the problems, you're like, 144, you just start breaking it down right away and you forget that 144 is a perfect square. Well, here's what it would look like if you're doing a perfect square. This would be 2 times 72. This is 2 times 36. This is 2 times 18. 18 is 2 times 9. And 9 finally is 3 times 3. So I got a pair of 2's. I've got another pair of 2's. I've got a pair of 3's. And nothing single is left over. I can't use 72, 36, 18, or 9 because these ones already split up to something else. So I'm going to take a 2 outside from this group. I'm going to take a 2 outside from this group. I'm going to take a 3 outside from that group. Stupid lights. When I don't move around enough, the lights go off. There you go. Lights are back on. All right, so I've got 2 times 2 times 3. That's a total of 12. Nothing stays inside the radical because I didn't have any singles. And we should have known from the very beginning this was a perfect square. 144 is the perfect square of 12 because 12 times 12 is 144. All right, explain why the square root of negative 16 does not have a real answer. Real answer. So let's just talk about square root of negative 16. Remember what radicals meant. Radicals are what number multiplied by itself is this number. And you might say, oh, what about negative 4? But negative 4 times negative 4 is positive 16 and not negative 16. So there is no number that would multiply by itself and get a negative. Because anytime you multiply a negative by itself, your answer is positive. Anytime you multiply a positive number by itself, your answer is still positive. So you shouldn't be getting negatives inside the radical. So in this case, our radical has to be positive. So this does not have a real answer because the radical is negative. That is why there is not a real answer. Now, the real part is important. Later on, we're going to see that there are things called imaginary answers. I'm not making this up. There are imaginary answers out there that are just numbers that don't exist on the number line, but they still give us answers. But for right now, we're going to just talk about real numbers, and there's no real number that would be this. It's impossible to multiply a real number by itself and get negative 16. It just doesn't work. So for right now, we're going to say that that answer doesn't exist there. All right, solving equations by taking square roots. At the very beginning, we said that squaring and square roots were opposite operations from each other. So in order to solve this, what we can do is take the square root from both sides of the equation. Because square root cancels out squaring. They're opposite operations. So we get x equals, and then the square root of 25 is 5. But wait a second. That's not the only answer that works. Because if I square 5, yes, I do get 25. But if I square negative 5 times negative 5 is also positive 25. So that brings up the problem of that there's two possibilities for these problems. Anytime you take the square root of both sides, you have to take into account that if you squared a negative, you'd still get this answer over here that'd be positive. So we add the plus or minus sign. That just indicates that there's two answers, positive 5 and negative 5. Those are our two answers. Over here on the next one, if I take the square root from both sides, I would get x equals, and since I took the square root from both sides, I have to add the plus or minus to show that there are two possibilities. This number that we're squaring could have been positive, but it could have been negative too. And then we get root 40. Now, root 40 is not a perfect square. So we want to simplify this radical if possible. And I think we can because this is 2 times 20, not 10. And then 2 times 10, and then 2 times 5. So I got a pair of 2's and a 2 and a 5 left over. So our final answer is x equals plus or minus. The couples go out, so 2 comes outside, and then 2 times 5 stays inside. So this would be plus or minus 2 square root of 10. Last one. So we would take the square root from both sides. And we'd get x equals plus or minus, because I took a square root from both sides, and I get the square root of negative 81. But remember what we just said, these do not have real answers. So we're going to say that there is no real solution. Again, there's going to be imaginary solutions, but we haven't gotten to that yet. So for right now, we're just going to say there's not a real solution because you can't have a square root of a negative. It doesn't make sense for real numbers. There is one problem that I wanted to add on here because it pops up on the homework assignment that goes along with this section. When we do these problems, sometimes you can multiply radicals together. So let's just look at real quick 2 times root 3. Oh, it's supposed to be 2 root 3. Dang it. 2 root 3 times, there's it, 5 root 6. All right, so if I multiply these two numbers here, the coefficients, the numbers out front, they multiply with each other. So 2 times 5, that would give us 10. The radicals would multiply with each other there. So the coefficients only multiply with other coefficients. The radicals only multiply with other radicals. So we would get 10 root 18. And then we can split up 18 into 2 times 9. And 9 is 3 times 3. So we do have a pair of 3's down there. Now I already had a 10 outside. So when I take this pair of 3's out there, remember everything's a factor or being multiplied. So I'm going to take this pair of 3's outside and leave the 2 inside. So my final answer is 10 times 3, 30 root 2. All right, that is the end of the introduction to 5.2.1. You now can move on to lesson 5.2.1. Enjoy. Bye-bye.